3D primer. 3D graphics is all about representing shapes in a 3D space using a coordinate system. The renderer in Three.JS that we will be using is the WebGL renderer, and so we will focus in the course on the coordinate system used by WebGL, which looks like this. Other coordinate systems are common, such as Z pointing up, but in our course Y will always point up. Notice that assuming the viewer is looking down the negative Z-axis, then the X-axis extends to the right, the Y-axis extends upwards, and the Z-axis points towards the viewer. This arrangement is sometimes referred to as EUS, East, Up, South. If the camera was positioned high in the Y-axis and looks directly down, then the east and south directions are more obvious. Objects are defined using vertices. A single one is called a vertex. It's a vector value. If you're not sure what a vector is, don't worry, it's simple. A vector is simply a group of numbers. A single number is a scalar, but if we use two numbers together, then this is a vector. For a vertex, it needs an x, y, and z value. And so in Three.JS terminology, it's a vector 3. A vector with 3 numeric values. An object is made out of vertices and faces. Suppose we have a cube. This has 8 vertices and 6 faces. Each face has 4 edges. Imagine the top face of this cube has the vertices v1, v2, v3 and v4. A normal is a vector 3 property that stores the direction in which a face is pointing. The length of this vector is usually of unit length, that is, it's 1 unit long. And finally, a face will need to describe how it's coloured, possibly as a simple colour, or it could be by mapping an image onto the face. When an image is mapped, a 3D engine needs to know how to place the image on each face that uses it. To facilitate this, a vertex not only has to know the x, y and z values, it also needs to know the x and y value of the image map. This is usually called the UV value. This is a vector 2, a vector with 2 values. U represents how far left to right and V up and down. The UV value 0, 0 would select the bottom left corner of the image, while the UV value 1, 1 would select the top right. By carefully selecting the UV values, a 3D artist can map an image onto a complex mesh. In the 3D application, we load in our 3D objects and their materials, then we can move, rotate and scale them using the Three.JS library. You might be relieved to know that we very rarely have to be concerned about the underlying details of the mathematics that converts this into an image on screen. But in principle, WebGL uses shaders. A shader consists of a vertex shader and a fragment shader. The vertex shader moves the vertex into the normalized clip coordinates. That is, x, y and z are all converted into values between -1 and 1. Three.js has all the shaders you'll need for most things. In general, Three.js will do the mathematical heavy lifting. But it's useful to know that the library uses a matrix for the model that moves, rotates and scales it, another for the view, which takes the camera's position into consideration, and finally a matrix that projects this onto the 2D screen. As well as the vertex shader, we also have a fragment shader. This works at the pixel level. The fragment shader follows the vertex shader, and so it already has the vertices converted into clip space coordinates. The purpose of the fragment shader is to determine the colour for the individual pixel. The process of taking the 3D data and turning this into a 2D picture is often called the rendering pipeline and takes this form. So that's what's happening under the hood. But when you're creating web apps using Three.js, unless you want to start writing your own shaders, you'll be working principally at the 3D object level, so you won't need to worry about vertices and pixels. I hope this brief overview gives you an insight into what happens for all 3D apps, from visualizations to games. But it's time for us to look at creating our first Three.js app, and in the next video we'll do just that. Catch you in a minute.